which types of systems are we modeling? Well, when modeling all sorts of systems, it can be some kind of propulsion system for a marine application. It could be a robot, or it could be an aircraft, or an excavator, so on and so forth. So it can be a lot of different systems. But what we're looking at is the dynamics of the systems. What happens when I accelerate a car, or when I take a drug, how would that metabolize in my body, and so on. So basically, what happens over time when I'm doing some kind of action. See if my notebook works. Yep. And to accomplish that, we have the part of a visual graphical user interface with a SystemModeler, which has several different key features that I will walk through, like drag and drop modeling, multi-domain modeling, instant visualization, and so on. And we also have a connection to Mathematica. So SystemModeler stand alone from Mathematica. And the first examples I will give you are completely independent of Mathematica. But then on the second half, I will show examples of why would you like to connect to Mathematica. What could you do in case you have both Mathematica and SystemModeler? And I will, as I said, do this by example. So let's start by the first example, drag and drop modeling. Why is this interesting? So in Mathematica, you develop code, or let's see, let me load the link first. Oh. So in Mathematica, as I will drive this from Mathematica, I'll have to learn to type, sorry. Here we go. Okay, for some reason that would not open. Oh, okay, I know what. I haven't loaded library. You have that. There you go. So, component-based modeling. If we look at this model here, we have two different representations of the same model. At the left-hand side, we have an electrical circuit, as you would see it in a textbook. At the right-hand side, we have a block-based version of it, which is basically if you try to represent the algorithm in the terms of gains, integrators, and so on. And this is basically what you would do. I don't know what it's kind of moving here. It's your phone, perhaps. So on the left-hand side, it's basically the algorithm you would develop if you would type it in let's say, C code or anything like that. But on the left-hand side, you have the electrical circuit as you would have it in textbook, and also as you have it in SystemModeler. You can simulate these two by just clicking Simulate here. And without having to do any textual coding as you would do in Mathematica, it will simulate the two models. And I can go into any component, like let's say, the input voltage of my electrical source, and look at the current. It's like a sinusoidal current, not very spectacular, but that's what you have there. But I can also go to this block-based source and try to find the same kind of current in that, because this is a representation of the other one. But of course, it's harder for us to see what is the current of the resistor or the capacitor and so on the right hand. So it's kind of complicated to develop a model in a block-based manner or in a code and then try to see it. So that's why we work with components like this, in this case, a resistor, capacitor, and so on. And it's important also that it's not restricted to electrical fields. So the reason why traditionally you were working in these kind of, let's say, block-based domains was that you could do models of different domains, meaning it could be a mechanical model, it could be a hydraulic model, a biochemical model, and so on. It didn't really matter because it was just a mathematical representation. And then there was a bunch of tools where you could do this left-hand side model, electrical tool like SPICE, which was very good for some electrical circuits and so on. but you couldn't do kind of both a general model and still be component-based. But that's what you can do in SystemModeler. So let's show a model some other type, and let's go for a pendulum, like that. So in SystemModeler, there are several different libraries available with different types of components. Like in the Mathematica standard library that comes with the software, you can find components from electrical components, mechanical, thermal, and so on. And in this case, I'll doing a pendulum, and I will do a 3D mechanical pendulum, so I will use the multi-body library, which is a 3D mechanical library. If I expand here, there's a world object, and the world object is basically, let's zoom in, is basically an object telling which is the gravitation of Earth and so on. I can set up my environment, basically. And then to this, I will connect a joint, which, let me use the simplest possible, a revolute joint. And then to that one, I will have some kind of cylinder connected to it. So I go to the, let's say, a body cylinder like that, and I can connect these together with a connection line tool. So this is similar to how the electrical circuit was connected, but in this case, it's a 3D mechanical system. Now I can select different parts like the body cylinder, and I will see a list of parameters describing it, like, for instance, R, which is the length of it. I can set some length, 1, 0, 0, like that. And I have now set up my system. Yet again, behind the scenes, we have equations for this, but we don't really have to bother. We just have to understand which are the types of components that my system consists of. And then I can build that and simulate. And yes, as for the electrical circuit, I can access all the variables in each component, like the revolute joint, the body cylinder. Or in this case, as a 3D mechanical system, I will get a small visualization of the pendulum. It kind of behaves in an expected way. Then I can start expanding this model. Let's say that I want to have a triple pendulum instead. Like, make a couple of copies of that, like that. And really don't matter how I arrange things here. I connect that. So now I have a similar system, but with 3 different sections, so 3 different pendulums connected to each other. And I can simulate these. So I can start expanding, making my system more complicated as I want to advance. And in this case, the system would have 3 pendulums connected to each other. And as I have not added any kind of friction models or anything like that, we will see it behaving in a chaotic manner. Okay? So what happens if for instance, if in fact I have some friction, then I want to add that. So how do I add friction to this model? Well, I can do that by connecting a friction model to every joint. I can do that. I'll add a flange here so I can connect things, say true here, and we can see that it pops up 2 small connectors here, and that are connections to rotational mechanics. So now I can connect components from the rotational mechanics library, like a damper, which is basically friction, like this. Or I might perhaps want to add some actuation to this one, so let's change that also. Let's say, how would I actuate that? Okay, so let's do this. We'll see more of this library in next presentation, but it's a hydraulic library that we have added, where we have, let's see if we have examples of rotational actuators. There you go. Let's look at this one. Yeah, probably a good one. So this is a hydrostatic transmission. Doesn't really matter what it is. Let me create a copy of that and try to use just to show how I can connect things together. I copy that to my use classes. So this is a hydrostatic transmission. We won't go through the details of it. There's no time for that. But what I'll do is I'll add a connection here at the output side of my transmission, create connector. And that means now if I use this in the pendulum, like this, I didn't really place the connector very well. I can connect the transmission to my joint here. So now I have connected a hydraulic circuit to my mechanical circuit. And that will hopefully activate, hopefully, I'm not sure. It will hopefully work. So now I can simulate this. It says optimizing equations. So this is basically when it's generating the code that you would otherwise have to do by hand if you would like to code it for instance, in Mathematica. And now we can go and look at the simulation of this. And hopefully it looks slightly different from the previous version. And I forgot to set any parameter for the friction, so the friction is probably 0 or low. But still, you saw that it behaves quite differently. So that easily can add different parts, whether it's friction, hydraulic actuation, or whatever part you will. Yeah?
Do you need to assign some coefficient or number for the hydraulic system?
Yeah, the hydraulic system, as I just grabbed an example that was ready-made, probably all parameters are set there. I really don't know anything. I just grabbed an example that I haven't looked at before, so it has parameters set for all the valves and so on in it. Okay, so that's the most important feature of SystemModeler, to be able to drag and drop things together, and then that means you can do multi-domain models, so you can combine, as you saw, the hydraulic circuit with mechanical circuit. It could be electrical actuator and so on and so forth. And to help with that, you had the built-in model libraries where you have components that you can reuse rather than having to build components yourself. And also, as we're building up, so in this case, I added, I can actually, as I did it this way, I can actually illustrate. Hierarchical in this sense means that now we have the example model there that I reused, and that is used as one component. So I double-click into that, and I can see this is the system I'm using here. So hierarchically, I'm building up a system with components that become more and more complex. This system that I have built here might be another component that I add to another system to make it something even larger. So hierarchically, I can build up a very advanced system. I think I skipped that for time constraint. Yep. And of course, the model in itself is not that interesting. What makes a model interesting is once you start to analyze it. So it could be a simple model like this one, which is a model of a wheel. So wheels are we have used wheels for thousands of years, but still they're complicated to understand. And even this kind of simple example, where we have a wheel here, this is the wheel, and then we apply a constant torque on it, and it's attached to a center here with a revolute joint and can basically rotate around that. And when the centrifugal force becomes too big, then it will start to slide. So let's look at this, how this looks like. So this is what we would like to study. How would this behave when we apply this force? And it might be expected things or less expected. So in this case, what I will do is I will plot the position of the wheel. Let's take the drive wheel friction. See here. And choose the, so it was there. Was that really where I wanted to go? Let's close a little bit here. Close all but this. Nope. Oh, actually, I should go to the, let's look at the model again. It's the prismatic joint, frame A, I guess, and X and Y. Oh, that's of course the frame B should be the one. There you go. So now what we can see is how the wheel is, because of how the axis has been chosen here, it doesn't look like a circle, but it's a circle. And we can see that in the beginning, we have the wheel revoluting in more or less a fixed radius. And then after a while, it slips out and goes here. And actually, if I simulate for a longer time, let's go for 40 seconds or 60 seconds. I will see that it repeats this behavior actually. So now I can start to experiment and try to understand why is this happening. Anybody knows? No? So basically when it's going out here, the centrifugal force is going down. So after a while, it will be lower than, it will be low enough so the frictional force will be high enough to keep the wheel without sliding. But then it will start accelerating again because of this constant torque, and after a while it will slip. It's kind of, I would guess it's similar to what happens when you drive aggressively with your car. I really don't know, but it feels like it's kind of relates to that. So in a sense, that's all you want to do in SystemModeler. You want to build a model, whether that's, as in this example, a mechanical model or a biochemical model. You drag and drop that together, and you do some plots. And for that, you use the built-in libraries, or you create your own custom libraries. I think I will skip that. But basically, how you have the hydraulic component there, you can make your own versions, your own components, and reuse them in larger systems. And upon that, we'll have extra libraries that are not included in the software itself, but that you can download from a library store. And the hydraulic library that I used was one of those examples. There's a biochem library, a cooling library, and so on. And actually, I think I will return to that in the next as a library store is a new thing. But today, we had a new library called Model Plug that we launched. But I'll get back to that in the next session. So that is what you use SystemModeler for. And now you have done this. You can look at the plots. You can change parameters and see what happens. If I change the friction, how would the system change, and so on. But then, why would you have Mathematica? Well, Mathematica is there for several reasons. And for instance, to programmatically create simulations, rather than running the simulation as a different simulation center, I can use it as usual from Mathematica. OK, that link was not correct. Let's skip that. Let's go here instead. We will gain some time also on that. So basically, you can do things like running batch simulations from within Mathematica. Saying, yeah, like any Mathematica code, you can have, but there's a WSM simulate command. Let's try to find it instead. Don't know why that link didn't work. Let's go here. Where would I have that? It's probably there. Yeah. It's easier to understand what you would be doing. So you would have something like having a model within Mathematica and run WSM simulate, which is Wolfram SystemModeler simulate. And you can change things like, in this case, initial value, setting that to a range rather than a specific initial value. Or you can change parameters to a range. Or you can program that in any way you would like. So within Mathematica, set up the kind of simulations you want to do, whether you want to do a Monte Carlo simulation or what you would like to do, and then get results within the Mathematica environment. So here you will see a plot of a bouncing ball when we release it from different heights. So very simple, but it allows you to do a lot of experimentation rather than in like a command line, rather than having to try different parameters one after the other. You can also use it for control design. Have very limited of time, so I'll go rather than showing there. It could be model inversion control. So you would like to, did I lose internet connection? Rather than developing, yeah. Okay, so let's go back here. So rather than, when you develop the model, you want to develop a controller. So you had a model, then you can go to deploy the model into Mathematica and use Mathematica's control system capabilities to design the control system and then deploy that to the model, back to the model, and you have a model that will behave the way you like. So you might do something like this where you have a system, if in case you happen to know model inversion control is, you have a model that rather than, so you build a model of a system, and then you look which is the desired output. You invert your model and set that output as the input of your system, and you will see which is the input that replicates what I would like to. And then I can apply the input to my real system to control that and get my behavior. And this is one thing where you could use Mathematica for. So if we go back to the drive friction, as you saw that rapidly, you can do, I skipped through a bunch of things. It was sensitivity analysis, model calibration, model optimization, all sorts of things that you would normally do in Mathematica, you can do now with the models. So that's the idea. You could do things like more custom visualizations and plots of your system. So if we go back to the drive friction and look at that model from on the website here, we can see we have this system here, and you can create small CDFs like this one where you can study how does this behave. So you remember the plot of the wheel position. Now this is the friction curve where the slip velocity is the x-axis and the friction force is the y-axis, and that's how the friction works for well, different wheels have different frictions, but in this case, this is the model for the friction. And using this, we can now start to play around here and see that when we move here in time, we see we're in here. And that's, at the same time, we can see that the point here, the velocity or slip velocity is below a threshold here. And we can follow the point in all of these. We are in this green area here. And it's when we come to this orange area, let's see if I can hit that, like here. Oh, it was somewhere here in the orange area where I will start to slip. Because that's where my slip force, you will see it kind of decreases as the slip velocity increases. And as the slip force decreases, we will lose traction. At the same time, the centripetal force is increasing slowly. And we will get into this part where we slip here until we reach a point where the centripetal force is larger or smaller than the friction force, and will yet again start to revolute in a constant manner. And then we will slip again, so on. So Mathematica, I gave a very quick part of that. Mathematica is used to analyze your system, to design it, and to explore ideas. SystemModeler is used to develop the system itself and do initial investigations of it, basically, doing plots, doing 3D visualizations, and so on, and understanding better how it works. So with that, I'll leave for questions. Thank you.